Okay, so welcome everyone to the online Horowitz seminar. Today we're very happy to have Christophe Garban from the Université Lyon, who will tell us about the statistical reconstruction of the Gaussian free field and the Kosterlitz-Thouless transition.
Okay, so thank you very much, Ron and Asaf, for the invitation. I'm very happy to be in Tel Aviv today. Okay, so I will tell you about a link between a statistical reconstruction problem about the Gaussian free field in dimension 2 and a phase transition, which is a topological phase transition in dimension 2 called the Berezinskii-Kosterlitz-Thouless transition. And this is a joint work with Avelio Sepúlveda, who is also in Lyon, and who will be in Santiago in Chile next year. Okay, so my first slide is about spin systems in dimension 2. So the whole talk will be about models that are defined on the Z2 grid. So everything will be two-dimensional. And here I have 4 such models. So you probably know at least 2 or 3 of these, but I will review each of them. So they are all defined, as I said, on this Z2 graph, but the spin that is attached to any of these sites X in Z2 belongs to different spaces. So for example, in the case of the Ising model, the spin will be plus or minus 1 valued, or if you prefer, just a plus or a minus. In this model here, which is called the XY model, it's also called the plane rotator model. The spin will belong to the unit circle S1. Here, this is the GFF, or the Gaussian free field. The spins will belong to this non-compact space, which is just the real variables. And the last one, so here we see that there are 2 models that have discrete symmetry, which is the Ising case and this later case here, which is the integer valued GFF. So this one, you can see it either as the Gaussian free field conditions to belong to the integers. So here the values of the spins are in Z. Or you can also view it as an extension of the Ising model, but the spins are integer valued instead of being just plus or minus here. And we'll see that the 2 models in the middle, they have continuous symmetry. So this is the O2 group for the XY model, and this is the translations for the Gaussian free field. While the 2 models that are the further left and the further right, they have discrete underlying symmetries, and this will be important for the rest of the talk. And these 4 models, they share the same type of natural probability measures, which are Gibbs measures, or if you prefer, Boltzmann weights. And here I will be a little bit fast, but I wanted to give a self-contained definition. So the probability of any such configuration here. So in the discrete cases, it's simpler because these are probabilities. Otherwise, these are densities with respect to Lebesgue measures. But in either case, the probability of a configuration will be proportional to exponential minus beta, I'll get back to that, times the sum over the neighboring vertices of the gradient square. So here we see that when beta is very large, these probability measures prevent the existence of large gradients. So beta is very large. It's a little bit like having a temperature T which is very low. Beta will always be the inverse temperature. And in those cases, the system will be very ordered. So if I take the XY model here on the top, or the plane rotator model, it's the same model. When beta will be very large, the spins attached to the points on Z2 will fluctuate a little bit, but will look like that, like very ordered. Well, if beta is very small, if beta has a small value, it means the temperature T will be very low. Very large. And it means the system is going to be very disordered. Okay, so now I will review each of these 4 models to see what is the effect of this inverse temperature beta. So let me start with the simplest of these 4 models, which is this one, because it is Gaussian. So for this model, as I said, the probability of a configuration, or here the density function, is proportional to this exponential minus beta over 2 sum over the neighboring vertices of this gradient squared. And the important thing to notice here is that we have a quadratic form. And the fact we have a quadratic form here implies that we have just a Gaussian vector, in which place it depends on the graph. So for example, here, if I have an n by n grid, and later I will often call these lambda n square boxes inside Z2. If I have this n by n grid, I have a Gaussian vector here, which is going to be in R to the n squared. So I have a Gaussian vector, finite dimensional Gaussian vector. And in that case, it's easy to compute its covariance matrix, which has to do with the simple random walk in Z2. And for example, if I take the middle point here, if I take the middle point x0, I can look at the variance of that point. And it's easy to compute here that this variance is proportional to log n. And in this model, the effect of the temperature is the easiest possible effect. It's just a scaling effect. So the higher the temperature is, the higher the scaling is, the lower the temperature is. So it's in 1 over beta. And recall that 1 over beta is the temperature T, okay? So if you want, the variance is T times log n, and there is a 2 pi constant, but whatever that constant is. So what does it mean? It means this random surface, this Gaussian process, typically fluctuates like square root log n in the bulk, okay? So there is no phase transition for this model, but we'll see at the end of this talk with this result with Avelio, that from the point of view of the statistical reconstruction problem that I will introduce, there will be a certain phase transition for this Gaussian free field. So I will quickly tell you about the easing model, because the easing case is not going to be the focus of this talk. But here the state space was -1, 1 to a finite box, or -1, 1 to the Z2 grid would also be possible. And it was exponential minus beta over 2, sum over the neighboring sides of sigma I minus sigma j squared. So when T is very large, or when beta is very low, the system is very disordered. And what you see here is basically a TV screen. It's almost like a uniform measure on the hypercube -1, 1 to the lambda n. When the temperature T is going down, at a very specific point, which is the critical temperature, you will start seeing nice structures at all scales. And for example, by a theorem of Shelkak and Smirnov, these curves that separate the plus phase from the minus phase, they are known to converge to the SLE 3 curves. Okay, and if you keep lowering the temperature, if now beta is very, very large or T is very small, what you see is something which is very ordered. So there is long range order. Okay, so here the system has been prepared with plus on the boundary. I have stolen these simulations on the web. And what you see is that these plus boundary conditions is preserved all the way through the middle of the system. Okay, so I will just say a quick word on how does one prove long-range order in such systems with a discrete symmetry. If there is a continuous symmetry and you are on the Z3 lattice, there are other tools that some people in the audience know well. But if you are in 2 dimensions, you need a discrete symmetry. And the classical way to prove long-range order is this Peierls argument. And the way it works is, imagine you have plus boundary condition. My color is not good here because this should be blue. Imagine I prepared the system with some plus blue spins on the boundary. And I ask myself, what is the probability that in the middle here, there is a minus? If beta is very, very large, or again, temperature is very low, there is a entropy versus energy effect, which says that in order the spin in the middle to be minus, you need to have at least one interface gamma, which will surround that middle point. You may have 3 such interfaces or 5, whatever odd number, but you need at least one. And then you can check that the energy cost of such an interface is something like exponential minus beta times the length of this interface. And this is very costly. And then you can set up a combinatorial argument which tells you that there are not so many such gamma interfaces, and you can conclude that there is long range order as soon as beta is sufficiently large. Okay? Now, if you move to the XY model, such a Peierls argument will not work. So let us see a few simulations also stolen from the web of an XY model at large temperature T. So T here is very large. So large gradients are not so much of an issue when the temperature is large. And here the way it is drawn is that it is pictured here. On each point X in Z2, you have to imagine that there is a spin sigma X which lives in the unit circle S1. And that spin is colored depending on its angle in that way here. Okay, so now you still have something very disordered at large temperature, but it's more modern. It's a color TV screen. Well, it's still old TV, but colored now. Okay. Now, if you let the temperature T, if you let it go below, like to lower and lower temperatures, you'll start seeing pictures like that. And what you see here is that it's still not a long range order phase. The spins that are here are not much correlated with the spins that are here, but it's a somewhat nicer colored TV screen. Okay, and why cannot you do a Peierls argument? So this is a picture by Ivan Velenik from his book. So as opposed to the Ising case, if you prepare your system with a boundary condition which is oriented towards east, you may ask yourself, what is the probability under the Gibbs measure that I introduced at the beginning? What is the probability that in the middle you change your mind and now you are pointing towards west? In the Ising case, it was very clear. It was necessary that you would have an interface, a gamma interface, with a lot of energy cost along that interface. Here, it's a bit more subtle. It's possible that you may find a system which will continuously change your mind in such a way that the energy cost is going to be low. And it turns out that you can minimize that energy cost, and those minimizing spin configurations are called spin waves. And because of the existence of such spin waves, it can be proved that there is never any long range order. And this is a theorem by Mermin Wagner, which is very nice. And I know at least one person in the audience, Ron, who likes that theorem very much and implemented it in different cases. So I think that theorem is from the 60s or so. And I guess, I'm not sure, but I guess at the time people thought, okay, it's very interesting, but probably that means there is no phase transition whatsoever for this XY model in dimension 2. But in the 70s, 3 physicists came out with a very nice idea, very nice observation. They found out that even though the long range order phase is only here, so at T equals 0, which is a kind of trivial point here, yes, there is long range order because the ground states are all aligned to each other. There is long range order, but it's kind of trivial. But they noticed that there is a more subtle phase transition which can be described like that. When the temperature T is very large, then I didn't lie when I told you that it's like a TV screen. At high temperature, things are very much decorrelated. The 2-point correlation function is exponentially decaying. So that means the correlation between the spin here and the spin here is exponentially small in the distance between X and Y. Now, if you reduce T, if you go to smaller and smaller temperature, at some point, according to these three physicists, you cross a critical temperature, which is an infinite order phase transition, and which is called the KT or the BKT transition. And what's going on there? Below that temperature, what happens is that you still don't have long range order, otherwise Mermin-Wagner would be wrong. But what you have is called quasi-long range order. And what does it mean? It means that if you take 2 points, say that one and that one, X and Y, now the correlation between these 2 points, or if you prefer the expectation of the cosine of theta X minus theta Y, or the expectation of the scalar product of these 2 spins that belong to S1, does not decay anymore as an exponential minus the distance, but it's now a power law decay. And if you like statistical physics models in dimension 2, then you do like power law decay. For example, the easing model, if you look at it exactly at the critical point that was computed by Onsager, it is known that the correlation between sigma x and sigma y at far distances behaves like 1 over x minus y to the power 1/4. So in other words, this critical alpha for easing, it is 1/4 at TC of easing. So what does it mean here? It means that instead of having one critical model, we have a full line of critical models. All these things have power law decay, and all of these things should be different nice critical models in dimension 2. Okay, so now I want to spend not too long, hopefully, but I want to spend a little bit of time to tell you how the physicists found out about this transition. And then I will tell you even less on the way mathematicians proved such a transition. Okay, so the way physicists argued, I find it very nice. So they start with the definition of the model. So the probability of the configuration is proportional to this Boltzmann weight or this Gibbs weight. And now I will argue only in the case where beta is very, very large, or if you prefer, temperature is very low. So the first step here is just a trigonometry step. This I won't need to explain much. It's just computing what is the Euclidean distance between sigma I and sigma j. This is just given by the cosine between the angle at I, which I call theta I, and the angle of the spin at j that I call theta j. So now I just have this expression of the Gibbs weight in terms of cosines. And then from there to there, the argument goes as follows. If beta is very large, what you expect is that your system is going to be very ordered, as I've drawn in the very first slide. And if it's very ordered, if this is the site I and this is the site j, what you expect is that theta I is going to be very close to theta j. And if that's true, well, then, at least from a physics point of view, it's tempting to do a Taylor expansion. So you Taylor expand this interaction, which is in exponential cosine. And at first order, this is going to give you 1. So it's going to give you beta times 1 minus 1/2 theta I minus theta j squared. And then plus some quartic terms and so on. So the first thing to notice is that when you have a Gibbs weight or a Boltzmann weight, it's the same thing. The constant terms, they don't matter. In other words, when you have an energy profile, if you shift your energy profile by a constant, so the same constant for all the configuration, it doesn't change the underlying measure. It's just killed by the partition function. So I can remove that constant, and all what remains is this minus beta over 2 times the square of the gradient. And now, usually what physicists would do is they would say, look, we recognize the GFF, but if we want to prove anything, physicists would say that you also have quartic terms, which are theta I minus theta j to the 4, and some 6th order terms and so on when you do the Taylor expansion. And to make things a little bit more convincing than just saying, notice there is a GFF, they would start implementing a renormalization group analysis. and they would notice that the quartic, the sixth order terms, and so on are not relevant under the iteration of the renormalization group. So the argument that Berezinskii-Kosterlitz and Thouless had is a little bit different from a renormalization group argument. What they say is as follows. They say they also recognize that this Gibbs weight is the same as the Gibbs weight we had initially, with a little difference, which is that the theta I and theta j, they do not quite belong to R, but they should more be into the 0 to pi. Okay. And so what they say is that imagine you view your model in the continuum in R2, maybe you took some mesh going to 0. What you really have is a one form. So what the Gibbs weight looks at the gradient of the theta I, so it looks at d theta, and d theta is going to be a one form on R2. And what you want is to put a kind of Gibbs weight. Oh, I don't know why it removed. Well, okay. So you have a Gibbs measure somehow now on one forms. And then the argument goes as follows. One forms, they can come either from zero forms as the result of a differential of zero forms or functions on the plane. But it could also be that typically your one form here may not be exact. In other words, it may not only come from these zero forms, it may also arise from two forms via the codifferential. And when is that the case? You may have singularities in your R2 plane, like that one that I've drawn here. This is a singularity for your one form. And if you integrate your one form around that singularity, it will not give you zero. So it means your form is not exact. Okay, so then they argue that this probability measure on one forms, there is a contribution coming from the zero form and there is a contribution coming from the two forms. But a two form is quite costly energy-wise because it creates gradients at all scales here, and they compute the energy cost a little bit like in the Peierls argument. They compute that energy cost, and they claim that at temperatures that are too low, these simply are too costly and you don't see these at large scales. And then when you start making the temperature higher, suddenly the two forms come into the picture and you start having exponential decay. So that's the way they argue. And in a picture, so I cheated a little bit with the pictures because I took a simulation on the web and I stopped the Markov process a little bit before reaching the equilibrium. Otherwise, pictures were a bit less, were not as nice. But that gives the intuition underlying this XY model. And what you should see here is at low temperature, plus vortices and minus vortices should be close to each other like that. And so on. Okay, so that's the physics way of anticipating this phase transition, but then it took some time to be actually proved. And this was done by Fröhlich and Spencer in a very nice work from the 80s, early 80s. And there is a very nice survey by Ron and
Vital Kharash.
Thank you, Ron. Vital Kharash. That was very helpful to us on the proof by Fröhlich and Spencer of this transition. And so the next two slides, I'm going to go way too fast. I just want to give you a very small flavor of how it goes because the philosophy is a little bit different from what Kosterlitz and Thouless have done. This is related, but it's a bit different. And the only thing I want to highlight at the end of the next two slides is that there is a deep link between the XY model and the integer valued Gaussian free field. So it's impossible that you'll understand all the details. I just want to give you some keywords, but I won't do the math properly. What Fröhlich and Spencer do is instead of thinking about these, the energy cost of these two forms, they go into the Fourier world. So what they do is they have the XY model on Z2. And for each neighboring sites I and J, they have this this term of this interaction term in the Gibbs measure, and they take a Fourier expansion of that. So they take a Fourier expansion of the periodic function, which at theta associates exponential beta of cosine theta. So this is something which is periodic, like that. And they take the Fourier coefficients of these, which are a little bit nasty, unfortunately. Because these, when you do the Fourier expansion, these are case-modified Bessel functions. And amazingly, in their paper, they managed to handle this case, but they also handle a slightly simpler case on which I will focus more in this talk, where they say that it was noticed before their work, but they say that if you replace this interaction that I introduced at the beginning, the XY interaction, which is exponential beta cosine, by that interaction here, which looks awful, but what they do here is just the following. This periodic function, this exponential beta cosine that you have here, you can think of it at very low temperature. Let me change color here. You can think of it as when beta is very, very large. Here it's very, very close to exponential minus beta over 2 times theta squared. Okay, by the Taylor expansion that I used before. So what you're not very happy with is that this Gaussian is not periodic. So you can periodize this Gaussian by adding Gaussian on the top of all these 2 pi. So this is at 2 pi, this is at 4 pi, and so on, to have a periodic function with period 2 pi now. Okay, so if you replace this initial interaction by this periodized Gaussian, the nice trick here is that the Fourier expansion of this periodic function is just given by this simple weight, this Gaussian weight here. And if you wish, this is just Poisson summing formula. I don't have the right name now, but Poisson summing, something like that.
Poisson summation formula.
Oh yes, thank you, Ron. Poisson summation formula. So by that formula, you have a much nicer Fourier coefficient than these case-modified Bessel functions that are a bit a nightmare to work with. All this to say that if you change your model, if you take this villa interaction, but as I said, this villa interaction, when beta is very large, is almost indistinguishable from the initial XY model. So if you take that interaction, you have a simpler Fourier, underlying Fourier analysis. And then I'm going way too fast to the next slide. So there is some business here that you don't need to read too carefully. And what I claim is that there is a duality between this modified XY model, which is called the villain model. There is a duality between this and the integer valued GFF that I had drawn at the very beginning of the talk. It was this kind of easing model, except the spins were in the integers, except to be in the plus minus. Okay, so when you do this Fourier analysis on all the different edges, you end up with a dual model, which is this integer valued model. And let me just tell you 2 things about this duality. This duality has 2 effects. The first effect is that the integer valued field, this phi, will not live in the initial lattice, but instead it will live in its dual graph. Okay, so here it's not much of a big deal because we had Z2 and the dual of Z2 is still Z2, but you have to think that the integer value GFF lives on the faces of Z2. And the second, maybe more important difference for this talk, which is often confusing, it was very confusing for me at the very beginning, is that there is a temperature, there is an inversion of temperature. Inversion of temperature. In other words, the beta for the villain becomes a 1 over beta here. So you see here below you see here that the Gibbs weight is not exponential minus beta over 2 as it was for the spin model, but it's becoming exponential minus 1 over 2 divided by beta for the integer valued model. So in other words, the geometry of the low temperature villain model will be captured by the geometry of the high temperature integer valued Gaussian free field. And this is the only thing that we need to remember for the rest of the talk. We don't need any of this analysis for what remains. Are there questions about that? Because I only noticed now that there were some questions. I'm sorry. Seems people are happy so far.
It's okay, Christophe. I answered what was in the chat.
Are there questions about this duality? Okay, so this is just a picture of what an integer valued Gaussian free field is. It's not a great one. I didn't find a picture of an integer valued Gaussian free field in dimension 2, but maybe I didn't look carefully enough. I don't know. So this is just an instance of an integer valued in dimension 1. So it has Dirichlet boundary conditions. In other words, it has value 0 on the boundary of this unit interval. We're in dimension 1 here. And then the Gibbs weight is the same weight as before, exponential minus 1 over 2 beta. Beta is below now because of this inversion of temperature. And we still pay a quadratic cost for the gradient. Okay? So you have to imagine this picture in dimension 2. I have some sketches after, but so how does the proof by mathematicians work, or by Fröhlich Spencer? It aims at understanding the transition from this exponential decay to this power law decay at low temperature. And what they do is they go through Fourier, so this duality, and they analyze, they find a phase transition on the side of the integer valued GFF. And what they show is that if beta, so now this is beta for the random surface model, if the temperature of the integer valued is very large, or if the temperature for the, no, sorry, that was wrong. This beta, let me remove that. This is the opposite. This beta is the beta villain. So if beta villain is very low, it means that beta of GFF, integer valued GFF, is very large. So it means the temperature of this integer valued GFF is very low. And what you see here, a little bit like the Ising case, you see something which is very ordered. If you prepared your system with 0 boundary condition, the 0 will be will remain true always through the middle of the system because of a similar kind of Peierls argument, except you have spins in Z now instead of just plus or minus. So in other words, at very, yes.
The localized should be localized on the top right of the
screen. Oh yeah, you are right. Sorry, this is the localized phase. Thank you, Ron. So in other words, the very high temperature of villain here is related to a very low temperature phase for the 8th function, and it corresponds to a localized phase. And the main input of Fröhlich and Spencer is to prove that as the temperature of that surface gets higher, or as the temperature here of the spin system gets smaller, there is a localization versus delocalization transition. So at some point, suddenly, this random surface that lives in the integer delocalizes, so it starts fluctuating like that. And they can show that the fluctuation becomes, as in the Gaussian case, that is to say, square root log n typically, okay? So their proof of the BKT transition is through this model. And as a consequence, they can prove these power law decay estimate for the villain model. So what they show is a bit more quantitative than that. They can show that this point-to-point correlation exponents. They're basically like the Gaussian free field case. In other words, this Taylor expansion that the physicists did in the low temperature regime, as beta goes to infinity, is more and more accurate because this little mistake goes to zero. Okay, so the critical exponent is more and more like just the Gaussian, what the Gaussian free field would give, and the variance of their model in the bulk is more and more what you would have in the case of the Gaussian field. Remember, in the third slide, I had the variance of a Gaussian free field, which was not conditioned to be in the integers, and there was no epsilon here. Okay, so so what do we have now? So when we have systems that are critical in dimension 2, and I have taken pictures here of the easing case, of the percolation case, and here there is a uniform spanning tree. There were many works in the last 20 years to prove scaling limits for macroscopic either interfaces or objects you may assign to these critical models. So for example, here you have a spanning tree, which is known to converge to the SLE8. Here, the interfaces are known to converge to the SLE6 by the work of Smirnov and Kamiya and Newman as well. And here, by Shelkak and Smirnov, they are known to converge to the SLE3. And the underlying motivation of the work we have with Avelio Sepúlveda is to ask, when you have a spin system with a continuous symmetry. So here, this is the O2 symmetry. What kind of macroscopic structure can you assign to a spin configuration? Can you recover some macroscopic fluctuating fields or some curves or stuff like that? And so we do not solve this, but the model we consider allows us to list precise conjectures for the villain model. And these conjectures are based on this old conjecture by Fröhlich and Spencer, where they say the following: if you sample a villain model, so remember that in each site X in Z2, you have a sigma X in the unit circle S1. The difference with the beginning is that the Gibbs measure is not given by the sum of the L2 distance between the spin X sigma I and sigma J for neighboring points, but this periodized Gaussian along the neighboring sites, which is almost the same at low temperature. And what they conjecture is that if you sample that spin system, each spin can be represented by exponential I theta x, where theta x is the angle at x, which is well-defined modulo 2 pi z. Then at large distances, this complex field should be the same as the complex exponential of a Gaussian free field. So for those who like Gaussian multiplicative chaos, this object which is here is called the complex Gaussian multiplicative chaos. Gaussian multiplicative chaos. So in other words, they predict that the large scale properties of a villain model are the same as complex GMC measures. Okay? And what they have here is it's not just exponential I times the GFF, there is also a constant in front of it. If the intuition of the physicist without any renormalization group was accurate, it would just be 1/√of beta. But here there is a little change. There is beta star is also called the beta effective, which is the result of what you have after a renormalization group. Okay, so let me state the first result that we have with Avelio, which will not be the focus of this talk here. We can show that some bound on what is the effective temperature of the villain model. So we can show that the inverse effective temperature is less than what you would have with the Gaussian free field, but we also have some quantitative bounds on the contribution that come from the vortices. And at the very beginning, when I was reading these things, I thought that the intuition from the physicists would be that plus vortices and minus vortices would kind of pair together. This is true, but what this is saying is that even though they pair together, they still create the same fluctuations at the GFF, but just with an exponential minus beta instead of a beta. So vortices still produce lots of fluctuations. And this is not a surprise for physicists. This is seen under the renormalization group. And there were papers by Dimok Hurd and also Pierluigi Falco that go into that direction. The advantage here is that this is a non-perturbative proof. And a consequence of that is that we have upper bounds on the 2-point correlation function, which also show the impact of the vortices. In some sense, the very non-trivial bond here is more on the other side, which is the Fröhlich-Spencer bond, which tells you that this is bigger than a power law decaying 2-point function. So if you wish, we have bonds on the corrections in the Fröhlich-Spencer proof here. And let me give you a last implication in that direction, which is related to that one. If you consider the integer valued GFF, so as I said before, if the temperature of this integer valued GFF is high, you are in the delocalized region. So you expect your integer valued GFF to fluctuate. And Fröhlich-Spencer proved a lower bound on the variance at a point. And Mathwise last summer, the PhD student of Jen Ding, he managed to show that the maximum of this integer valued GFF is above log n times the constant. So in other words, it's a little bit like in the unconditioned case, the maximum is also constant times log n. So what we can show with Avelio is the other direction. So maybe I should say that, especially here in Tel Aviv, so in the last five years or so, there were many deep works that studied the maximum of Gaussian free fields by Biskup and Louis-Dor and Hofer. I don't know if Hofer is online. Hofer and Elinan Shubag and so well, there were many works on the max of the GFF. So here, when you condition that Gaussian free field to be integer valued, we know much less. So Mathwise did the first step of saying this must be pretty high, like in the Gaussian case. And what we do is we use our improved spin wave estimates to say that the maximum will sit below where it would be if you had just the Gaussian free field, the unconditioned case. So if you think of the one-dimension case, it's not very surprising that it must sit below square root of n in the case of one dimension. In the two-dimension case, I'm not sure it's very surprising either, but proving that vortices have an impact on the max of the GFF, of the integer value GFF, I think is somewhat interesting. Maybe let me also tell you something I learned this morning, that a few years ago, I think it was 2014, I think Lubetsky, Sly, and Martinelli, they have very accurate understanding of the max of the integer valued GFF when you are in the low temperature regime. And I think they have the exact constant, which is probably 1 over square root of 2 pi beta. And then they have square root log n. So the max is smaller at low temperature because of the localization, delocalization. And then they have log n. So somewhat interestingly, so it's a times here. Somewhat interestingly, at low temperature, the vortices, anti-vortices, they don't have any contribution. And at high temperature, they change drastically the behavior here. Okay, but I will not talk more about this. The main focus of the talk is rather the following statistical reconstruction problem. So imagine you sample a villain model here. So sigma x, a villain model. By the conjecture of Fröhlich and Spencer, you expect that this field behaves like exponential, maybe I'll do it here. It should behave like exponential I 1 over beta star times a GFF phi x. So the question we ask is, given a free field phi x, if I produce exponential I t phi x, where in the rest of the talk, t, one should think of it as 1 square root beta effective, but I didn't want to carry this 1 over square root beta effective. If I give to you this complex multiplicative, Gaussian multiplicative chaos, but in the discrete case, can you recover what was the initial field? So in other words, if you're given this villain model and you believe in Fröhlich-Spencer theorem, can you recover, can you lift, it's a sort of lift procedure, can you lift this picture to recover what was the macroscopic GFF behind this picture? Okay, so in the rest of the talk, we will take phi GFF with just no temperature there, just a normal GFF. The temperature will be here, will be a scalar constant in front of it, which will be here. And the question we will ask is, what is the law? Can one recover the free field given this complex exponential? And it's the same question as asking the following. If you're given the Gaussian free field modulo 2 pi, the values of the Gaussian free field, but modulo 2 pi over t, can you reconstruct what is the initial field? Okay, so I will ask law of phi given phi modulo 2 pi over t. And to get some intuition on what's going on, I've drawn the one-dimensional case. So what is a Gaussian free field in D equals 1? It's just a simple random walk on Z, or here I have a Dirichlet case where this is 0 in 0. So this is a simple random walk on Z, which starts at 0, and it has ID increments, which are unit standard Gaussians. So a GFF in one dimension, this is just a simple random walk with Gaussian increments. And now the question I ask is, imagine you know your process, but only modulo 2 pi over t. So let us draw what it means. I have this 2 pi over t here, and I know the exact values of my random walk, but only modulo 2 pi. So 0 modulo 2 pi over t is 0. This is here, 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 here. Ah, no, so that value is here. I want to draw it into the interval 0 to pi, so I draw it here, okay? That's my way of drawing. There, so there it's away from my interval, so modulo 2 pi over t, I keep track of that information. Okay, and so on and so forth. So here I keep track of that and so on. And so the information that I will keep track of, and then I will ask myself, can I reconstruct the initial field? I will call it A, which is the field on the one-dimensional lattice now. It will be on the two-dimensional lattice later, which is made on all the values phi of x, but modulo 2 pi over t. And this will be a random field, which in some instances could be understood as a quenched disorder. I will get back to it later. It would be a quenched disorder in this 0 to pi over t to the power all the vertices in your graph. Okay, so now the question is, now that I have built this phi modulo 2 pi over t, imagine you're given this information. Can you recover what is on the left, which is the true simple random walk? So let's see how it works. So you have the Dirichlet boundary condition, so you know here there is no mistake, there is no possible mistake. And then you want to start recovering the initial path. So the only thing you know is that you know phi modulo 2 pi over t, so your initial random walk could have been here, or here, or here. So it's something like that. But probably the most likely that it was here, because you still have this quadratic cost for the gradients, which is behind the scene. So you don't want to pay too much gradients. And I will get back to it later, but in some sense, here there is a, so if you keep going, what you know is that your initial field lives in shifted copies of the integers. Okay, so for any point here, for example here, your field needs to be, if this is the point x, your initial process must live in A of x plus 2 pi over t times z. And the point just below lives in some other shifted copy of z, okay? So if you want to reconstruct your initial field, you will have to deal with a kind of integer valued Gaussian free field, except the fibers, the z fibers, they are shifted by some disorder now, okay? So, so given that quench disorder, I claim it's not hard to see that almost surely there is a unique ground state. Namely, given that a quench disorder, there is a unique path which minimizes the Dirichlet energy. So I think here it would be that path, and you can keep going on the whole line. This is the minimizing energy path on Z. But of course, I made my simulation, it's not a simulation, I cheated, but I made my path in such a way that taking the ground state doesn't work because I missed this step, which in fact costs more energy, okay? So now I will go quickly to this slide to say that the tool in order to apply a reconstruction process will be this measure on the shifted integer valued GFF. So it will be a measure on the in dimension 2 on a random 8 functions, but these random 8 functions will live in shifted copies. So my drawing is terrible, but shifted copies. So you have to imagine, I'm on the window now, that you have your 2-dimensional lattice, and on each vertex of the lattice, you have a copy of Z which is shifted. And you have to try to guess where was the initial field. Okay, so just to imagine a little bit what it looks like. So this is a picture by Ellen Powell. And I forgot to say that before I had a picture by Adrien Cassel. So if you imagine here that the temperature T is very large, it means you know phi modulo 2 pi over T, and 2 pi over T is going to be extremely tiny. And I will state a statement in a second, which will say that in that case, it's impossible to recover what was the initial field. So there will be a phase transition there. And when T will be small enough, 2 pi over T will now be bigger, but it's still something which is finite. And remember that as n goes to infinity, if this is the n by n lattice, so if this is lambda n, the point in the middle, it's in the initial Gaussian free field, it still fluctuates like square root log n. So this is finite. And what we show, I will write the statement in a second, is that when T is small enough, we can recover exactly where is this Gaussian free field here. Okay, so maybe I will give you the statement. So since there is not much time left, I will cheat. I wanted to do something handwritten, but I will, it's not very good, but I will cheat by taking the slides, the handwritten that I had, that I gave last week in Geneva. I'm sorry, it was a longer there, but I will use this if I manage. Sorry. Yes, good. So I will still scribble. Okay. Can you see it well enough? Okay, so I'm sorry, I wanted to write all that, but it's going to take me too long. So the statement is as follows. So this is the first result. if the temperature is, let me take something like that. The first result is that if the temperature is small enough, and I write it T break minus here, it's because we don't have a monotony property which gives us a unique critical point. So we just know that if temperature is low enough, something happens, and if temperature is large enough, something else happens. So the main statement is that if the temperature is low enough, then we can recover the field given that partial information phi modulo 2 pi over t. So what does it mean? Let me give you two statements. The first one is that if you take this n by n box here, and you take the middle point x0, what we claim is that there is a recovery function f of x0, which depends on, which takes as an input this partial information, call it either phi modulo 2 pi over t or the complex exponential. And that recovery function is such that if you take your large n by n box, then you can lift the partial information to know exactly where you are in the bulk. But there is a little mistake, which is of order 1. Why? Because at the very last step, as we had in the one-dimensional case, it's always possible that you make a little mistake for the last step, or maybe in the neighborhood of length 10. And what arises from the proof is that this big O of 1 correction also tends to 0 when the temperature goes to 0. But the point is that when t is 0.0, when t 0.5, say, we don't have Schrödinger fluctuation. We can really nail it down to big O of 1 fluctuation. So we can recover where it is. And if you want a little O of 1 statement, you need to take functionals that are a little bit more smooth than a delta functional. So imagine you take a function f on your n by n grid, which is rather smooth. I will not give details. Then I claim that you can reconstruct, given exponential it phi, what is phi n tested against that smooth state function, but now it's only up to little O of 1 fluctuation. The second theorem, which is just the same theorem, but it's the higher temperature phase, is the fact that if now T is too high, so bigger than something which should be just one critical point, but we may have some interval in between, we don't believe that, then we show that whatever recovering function you may try, whatever f of x0, you will never manage to capture what was the value of your field at x0. So in other words, the conditional variance is always going to be larger than constant log n. And this is uniform in the size of the system. And well, I'm already almost out of time. So can I have 2 minutes? Or?
Yes, please.
So I'll try very quickly to give a sketch of the low temperature phase of why can you recover such fields even though you only know the values in this finite interval 0 to pi over t. So what I want to say is that on this lambda n grid, n by n grid, you have 4 objects you may play with. The first object is the information you're given, which is this phi modulo 2 pi over t. A second object of interest is this object in orange, which I call the ground state. So it's unique, and I've drawn it here. So it's somewhere above your n by n box. And maybe the ground state is the function we want to use to recover where the field was. It's probably a good candidate. But we don't manage to control what the ground state is doing. And in some sense, the quench disorder here is too far from a symmetric ground state to use theories like Pirogov-Sinai theory to handle the behavior of ground state. So we don't manage to control where the ground state is. But what we can control is the behavior of the conditional expectation. In fact, the conditional expectation is going to be our recovery function. And the fourth object we have is the initial field, which we don't know. So if we view all these fields together, we have the ground state in orange here that we expect is close to the initial field, but this we don't know how to prove. And there is this conditional expectation. And this, our theorem is that this is very close in average to the true field, which I've drawn in blue, which is the Gaussian free field. So our way to say that there is a recovery is to show that in average, the conditional expectation is close to the initial field. And so what we show is this. We show that, for example, if you take a point in the bulk, the conditional expectation will never be far in average from what you want to recover. And to show this, it's not very hard, but I think interesting examples of an annealed Peierls argument. If you know all the settings where there are annealed Peierls argument, please tell me. I don't know such example. So why an annealed Peierls argument? This variance, we can write it classically as 1/2 expectations of phi1 x0 minus phi2, where these are Gaussian free fields that are conditionally independent given this partial information that we're given. And then I'll just say it in one word. What is the main part of the proof? Given these two GFF, which are conditionally independent given exponential IT phi, the goal is to say that both of them start at 0, because we have Dirichlet boundary condition here. And the whole game is to say that they keep being equal for a very long time. And now, as in the very beginning of the talk for the easing and then for the integer valued case, you want to show that having interfaces where phi1 and phi2 start disagreeing is something which is costly. And our argument here uses a lemma like that, a small lemma that we prove aside, which says that creating large gradients on any whatever subset is costly for the unconditioned GFF. And then the proof goes as follows. If phi1 and phi2 disagree in that region here, maybe I change color, if they disagree in that region here, it must be the case that around that region here, you will have a gamma interface, and that gamma interface will be either produced because of large gradients for phi1, which I've drawn in purple, or large gradients for the other one, which I've drawn in green. And these two large gradients must altogether produce the gamma interface. They may overlap, but you cannot have any holes. And then you have a kind of Peierls argument with combinatorial argument with these two colors, which tell you that this is too costly to create big interfaces. I won't say more, and I will just say one line for Ron, maybe, for the high temperature case. In this high temperature case, to prove that recovery is impossible, we generalize the Fröhlich-Spencer proof of delocalization of the integer valued GFF. But in this setting where we have this quench disorder because the fibers are shifted. And the technical issue here is that in the proof of Fröhlich-Spencer, there is a very important Jensen step at some point, which uses symmetry, and we don't have that one. So we have to deal with that. But I think I'll stop here. Yeah. Well, sorry, maybe just if you're interested, just after the talk, I can tell you motivations with recovering SLE4 out of a Villain model and some other works, like works that Ron has done with Spinka and other people about similar phenomena for random 8 functions, but are not quite the discrete Gaussian field, but are homomorphisms in Z and things like that. So I had more remarks, but I'm already too much out of time. Thank you.
Thank you very much, Christophe. Thank you very much. Questions, please, to Christophe. I saw at least one. JPC, you wanted to ask something? You can turn on your microphone and ask.
Yeah, so I would just type the question in the chat box. I was wondering this reconstruction critical temperature, does this whole machinery suggest that it is related to the BKT transition temperature?
Yeah, so that's a good question. So, so indeed, it's tempted to guess that, so first of all, I'm pretty sure there is one phase transition there. We don't have the monotony property, but I'm sure there is one phase transition for the statistical recovery problem. You may define as the infimum of T such that the variance is not log n anymore. But assuming there is only one, well-defined phase transition, in the paper with Avelio, we make a precise conjecture on what should be that value, because it should be related to the 8 gap of the Gaussian free field, the continuous Gaussian free field, and worked by Dubeda, Schramm-Sheffield, Miller-Sheffield, and so on. So I think it's quite convincing to have one precise value for when the statistical reconstruction should break. And indeed, it should be related to the Kosterlitz-Thouless transition, but that I'm a bit less sure. It should be very close to it, but I wouldn't bet that there is an equivalence between reconstructing the GFF and because the problem is in the Fröhlich-Spencer conjecture. At large scales, it should be the GFF, but not quite at small scales. So the little fluctuations that would not be exactly Gaussian at the small scale of the Villain model, they may have the effect of changing a little bit that temperature. So I would guess they're very close, but there is no reason that they would be exactly equal.
Other questions, please.
I'm happy to, even by chat or to have questions, if you have.
I wanted to ask a question. So you also mentioned that you understand that the vortices change a bit some of the properties of the model. For instance, that this beta star is shifted by e to the minus beta, and the maximum is shifted by e to the minus beta. Could you say a word about the techniques for that?
Yeah, so that's still in progress. But the way we do it is so what Dimock, Hurd, and Pierluigi Falco would do, it would be more for the sine cordon model when Z would not be too high, and they would run this renormalization group, and then they would keep track of the effective constant and how they evolve under the renormalization group. Here, the technique is completely different. What we do is we have a kind of algorithmic way to produce what is the Coulomb gas. So the nice feature of Villain, so our proof would not work for the XY model, is that there is a decoupling between the spin wave, the GFF, and the Coulomb. And we have a kind of algorithmic way of sampling the Coulomb, which allows us to have bonds on their fluctuations. So it's non-perturbative in that sense that we don't need to run the renormalization group.
I see, thank you. There are some questions in the chat. Maybe Gautier, would you like to ask your question by voice?
Oh yes, so good question. So maybe yes. I'm even on the good slide for that.
Yes, exactly. That's where the question comes from.
Okay, good.
But please ask your question by voice. I'm not
yes, so that people can see. I mean, it's related to. I mean, there's this sort of. I guess it's the L2 phase where the complex multiplicative chaos sort of exists, and I wanted to know if the recovery temperature is related to this phase or not.
Yes. So indeed, so in our case, we're only in the discrete, but you could ask the same question of recovering the GFF in the continuum given exponential I beta phi. So something like that. Can you recover phi? And if you were to do that, it would be a little bit like in this work of Nathaniel Berezinskii, Scott Sheffield, and Shin-Sun, where they recover the free field out of the real chaos. So here you have to struggle a little bit more because of the complex case that you lose the modulo 2 pi over t, basically. But I guess it's feasible. I think there are people working on this right now. And the difference with our work is that most likely there will be an existence phase where you can reconstruct. And probably that reconstruction can go all the way to beta squared equals 4 pi. I think this is our guess. Namely, all the way until the complex Gaussian multiplicative chaos is defined. But after that threshold values, the martingale is no longer uniformly integrable and there is nothing left. So in other words, what we believe is that there is reconstruction all the way to the range where you can build those complex multiplicative chaos. And then, well, it's not defined anymore. So there is no notion of Kosterlitz-Thouless transition in that sense. After, you cannot make a precise notion of reconstructing or not because you don't have that multiplicative chaos anymore. So there is a slight subtlety here that there is something between 4 pi and 8 pi that the sine-Gordon field is still well defined, but not the multiplicative chaos. And so we discuss a little bit this in our paper, if you're interested.
Okay, thanks.
Thanks, Gauthier.
Wei, would you like to ask now?
Hi. So, right. So I'm wondering that because, you know, you state this recovery transitions, it sounds a bit like some kind of, you know, percolation properties. So I wonder if you're starting with the these complex GMC, can you embed a dependent percolation model, maybe still FKG or so that, you know, so that you can rephrase that in terms of a percolation property?
Yeah, so it's a good question too. So I think in some sense, the proof that we have here has the flavor of a percolation proof because we sort of said that one edge having a disagreement between phi 1 and phi 2 is costly. So in the end, it's a kind of percolation argument which allows us to recover the process. But it's an annealed argument. So maybe your question is more about a quenched recovery. And that in that case, I don't know.
Okay, thanks.
Christophe, what do you mean by saying it's an annealed argument? You are conditioning on the information you get on the disorder, no? And running the Peierls argument given that information, no?
Yeah, so I always get confused with quenched and annealed. In that case, I think it's an annealed argument in the following. So it's a quenched reconstruction, because indeed you condition on that quenched disorder, that quenched information. And from that quenched information, you reconstruct what should have been the initial field with this reconstruction function, which is the expectation, the conditional expectation. So this is a quenched reconstruction, but I want to say that the proof is an annealed one in the sense that it says that this reconstruction function averaged on the quenched disorder is usually very good. But it's not that point on point we can say, on that realization, this is going to be good, the realization. And the Peierls argument is really using the average with respect to the underlying GFF.
Now I understand.
Otherwise, we would control the ground state, maybe, which we don't.
Very good. Thank you very much. Are there any other questions to Christophe?
Thank you, Wei, by the way, for the question.
Okay, if there are no other questions, perhaps people would like to unmute themselves and give a big hand to Christophe again for a great lecture. Now, the seminar is basically over, although I would be happy if Christophe does not mind going over the last slides, and I don't know if you mind or don't mind, so I can continue recording, and those people who want to stay, at least me included in that, can stay to see the last slides. If you wish, Christophe, what is it?
I will be happy to.
Yes, well, yes, then for me that would be great. And those people who want to hear can stay, and those who need to go can go. But I continue the recording.
Well, maybe it can be more informal if you.
It is up to you, Christophe. Maybe the audience watching at home might also want to see the last slides, but if you prefer, I can turn off the recording. It is up to you.
Yeah, let's turn it off so that everyone can ask and it can be more.
Okay. So thank you, Christophe. We'll continue the last slides offline, but the slides will be on the website of the seminar, so anybody can watch them on their own as well. So I turn off the recording.